Good evening, one and all. Myself, Yashvi Sheth, uh, your TA for the course Basic Calculation Principles and Calculations in Chemical Engineering, taught by Professor Subrata Majumdar from IIT Guwahati. Today, it is the fourth live session for the course, and we can now start the session. I will share my screen. So, starting with the brief of what was taught the lecture uh, in the lecture 11. So basically the lecture covered was ideal gas equation of state and various laws. Now this is the most basic equation which you use for in chemical engineering. So what does ideal gas equation of state mean? Now ideal gas means ideal gas is the gas is any gas that has no molecular interaction. So assumption for ideal gas is there exists no molecular interaction. So in that case, if you have any system, say for example, there can be reaction happening, or uh, there can be just unit operation taking place. So there will be some parameters with which are related to it. It can be pressure, volume, temperature, number of moles. Okay, so based on these values, if you are changing from state 1 to state 2 through any some process, okay, where you have this as 1 P1 V1 T1 N1. If you change the pressure of the system, let's say to P2, and you allow change the temperature also, then what will be the effect on volume? Moles will remain same actually. So what will be the final variables? So ideal gas equation of state is one such equation which allows you to relate pressure, volume, moles and temperature, which are the intrinsic properties of that particular system. So how is it related? Pressure is related to temperature, directly proportional to temperature. Pressure is inversely proportional to volume, and pressure is directly proportional to the number of moles. Okay. So now if we combine all this, pressure is proportional to T into N by V. And if we remove this proportionality constant, what will remain is PV equals to N RT, where R is the universal gas constant. Okay. And it is a constant here. Now, depending on the values of pressure, volume, moles, and temperature, all you can have variety, or you can have different values of R, or the universal gas constant. So these values of R are mentioned here. Okay, so based on what unit of pressure, volume, moles, and temperature you use for calculation, based on that you select any of the value and use that value. Now, another important terminology or law that was highlighted in the lecture was Dalton's law. So, for example, if you have a closed system and you have a n components present in it. Now, based on the number of moles of each of the component present, let's say it is N1, N2, N3 up to N, okay, there will be some corresponding pressure which is exerted due to each one of it. Sorry, it isn't. These are moles, these are pressures. Now, pressures due to individual species. Uh, the number of moles and pressure are directly related, and for gas, pressure is also an indication of concentration, right? So what you do here is, say for example, if you take an individual pressure for component 1 or 2 or any such component pi, then in that case pi is nothing but known as the partial pressure of that species I. Okay, so partial pressure is nothing but pressure of individual component in a multi-component system. So now if you have pi as the partial pressure of each species, then what will be the total pressure? In that case, total pressure will nothing but the addition of all the pressures, because pressure is an additive term. Now, in that case, how is P1 or any PI calculated? So, as I said earlier, pressure is nothing but a kind of concentration. So, PI, you can relate it with the total pressure of the system, which is PT, with, with this equation. So Pi of any individual species is nothing but Pt, that is total pressure, into the mole fraction of that component which is present in that system. Okay, so by this equation you can calculate it. Similarly, there is one more law which is Amagat's law. Now this law is for volume of gas. Okay, volume is also additive. So here you just replace pressure by volume. So the total volume, because say for example, if you have two liquids which are miscible and you add 100 ml of water and you add 100 ml of milk. So volume of the total volume will be additive. It will be V1 plus V2. So similarly for gas also, what comes out to be is V1 plus V2 up to Vn gives you the total volume of the system. Now, how do you find the individual volume of each component? It is nothing but individual volume is Vi equals to total volume into the mole fraction. Now moving forward to the next lecture, what it talks about the non, just a second. So in this lecture, what is discussed is for non-ideal gas. What what does ideal gas mean? It does not have any interaction between two molecules. Okay, so which is not the actual case. Now if you have any gas present in this atmosphere or so, then there will be some amount of interaction or collision. Just a second. So there will be some amount of collision or interaction, or there can be some van der Waals force of attraction also between two molecules of gas. However, we do not consider any force of attraction or any interaction for ideal gas. So there is no such gas which does not have uh, any interaction between two molecules. So all the gases that are present in the atmosphere, they are non-ideal. But at very low pressure, since the molecules are very far away, then what will happen is the any gas, you can consider it as ideal gas at very low pressure. This is because at lower pressures, what happens is the interaction between two molecules decreases because the molecules are very far from each other. So due to that, you can consider non-ideal gas to be ideal. Now, the equation of state which was used for ideal gas was PV equals to nRT. Now, for non-ideal gas, you use a correction factor which is Z, ZnRT. Now, this Z is compressibility factor, which is a kind of parameter or constant which represents what type of interaction or the amount of interaction or forces that are present in the gas. Okay, so the value of Z lies between 0 to 1. 0 to 1. So this is the range of value compressibility factor. Now this Z is always a function of the critical temperature, critical pressure, and the temperature. Like TR is nothing but T by TC, and PR is nothing but P by PC. So this is how Z is related to these terms. Now another terminology that was discussed in the lecture was critical temperature and critical pressure, because all these parameters they are somewhat related to these critical temperature and pressure also. So what does critical temperature mean? Critical temperature is, say for example, if you have a system in which depending on the conditions of temperature, pressure and it will have some state. It can be either in solid form, it can be in liquid form, or it can be in gaseous form. Okay, so if you at constant temperature, if you increase the pressure, then the gaseous will convert into liquid and further to solid. Similarly, at constant pressure, if you decrease the temperature, gas will convert to liquid and then to solid. Okay, and vice versa also applies. Now there comes one temperature at which gaseous molecules are so far away that you are no longer able to identify the molecules, or no longer able to identify the gaseous molecules. And if you further increase the pressure, because increasing the pressure liquefies the gas. Now if you still keep on increasing the pressure or pressure, then there will be no liquefaction. So this is the temperature above which there is, regardless of what pressure you exert, even if you increase the pressure too much, then there will not be any liquefaction. Okay, similarly the pressure corresponding to that point is nothing but critical pressure. So critical pressure is nothing but, if you want to liquefy a gas, then you need some at a constant if you want to liquefy a gas, then this is the minimum amount of pressure that is needed. Now this is denoted by TC and this is denoted by PC. Now for non-ideal gas calculations, you use this equation. Usually this is the general form of equation. Now there will be some correlations by which you calculate the value of compressibility factor. This parameter is known as compressibility factor. So there will be some correlations which are already existing, and based on that correlation you calculate this compressibility factor. Now this compressibility factor is all dependent on this critical temperature, pressure and all. So there are various equation of state which is available in literature, which are empirically derived and based on some experimental values also. So there are certain equations like van der Waal equation of state, virial equation of state, then there is RK equation, SRK equation, Feng-Robinson equation. Okay, so here I have just highlighted one of the equation. How does it look? Say for example, virial equation of state. So the Z is related to volume in this manner. So here you calculate the values of these constants from these equations, okay, and you put up the value of that constant here, and you calculate the value of z. So here this virial equation of state is iterative in nature, so you start with putting up the value as for ideal, and then you again calculate. Now starting with the assignment, first question is which one of the following values is the universal gas constant? So you have to remember the values of universal gas constant, and joule per mole per Kelvin is the most basic and it is the SI unit. So this unit you should remember, and its value is 8.314 joule per mole per Kelvin. Uh, Next question is, for real gases, the correct formula for van der Waals equation of state is dash, where these are pressure is P, etc. So the correct form of equation represented here is this. Now, general equation is nothing but PV equals to nRT. There is some correction in volume, okay, so and some correction in pressure. This is the pressure correction, and this is the volume correction. So what does this constant signify here? A is the van der Waals constant that measures the attractive forces between molecules, because depending on the attractive forces between the molecules, there will be some change in the pressure value. And also B is the correction factor for volume. So this is how like this constant you will get from the literature, or there are some correlations as I mentioned. So there will be some correlations from which you can calculate the values of this A and B, and you can put up this values here, and you can relate pressure, volume and temperature. Moving forward to the next question, the ideal gas equation can be written as. So now this is the most basic question, like you need to remember this equation at least. If you are not able to remember any non-ideal gas equation of state, then it is okay, it will be mentioned, but you should remember this. So what is that equation? It is PV equals to nRT. Now I have earlier in this lecture already explained how pressure is related. Pressure is directly related to temperature and number of moles, while pressure is related to 1 by volume. So if we combine, pressure is proportional to T into N by V, and removing the proportionality constant and adding a constant, we will have PV equals to nRT. Now the next question is, the gas having a pressure of 3 bar, just a second. The gas having a pressure of 3 bar, okay, so pressure here is 3 bar, temperature, this is 1, temperature T1 is 0 degrees Celsius, which is, so you have to remember one thing, whatever like it is always advisable, like temperature is usually measured in Kelvin, so it is 273.15 Kelvin, Okay, so T2 is, it is heated from 0 to 550. Wait a minute. Yeah, so it is always advisable to have a pictorial representation. So this is state 1. P1 is given as 3 bar. T1 is given as 273.15 Kelvin. Let's say it is having V1 volume. It is heated to temperature. It is state 2, let's say. It has T2 equals to 550 degrees centigrade, and P2 we don't know, and we have some value V2 which is 1/3 of its original volume. Here it is given. Okay, so V2 is 1 by 3 V1. Now T2 is 550 plus 273.15, which is nothing but 550 plus 273.15 comes out to be 823.15 Kelvin. Now here what we have, we are given is, we are not given anything about whether the gas is ideal or not. So you can assume it to be ideal if it is not mentioned as real, and you can use ideal gas equation of state PV equals to nRT. So here what happens is there is no change in the number of moles. Okay, so you can write for state 1 as P1 V1 equals to nRT1. And for state 2, you can write as P2 V2 equals to nRT2. Now you want to find P2, like you want to find the final pressure. So if we take the ratio of these equation 1 and 2, P2 V2 by P1 V1 equals to nRT2 by nRT1. Now both these get cancelled out, nr, since they are constant for this case. Now if I put up the values, then what comes out to be is T2 is 823.15 divided by T1 is 273.15 into P1 is 3 bar divided. Now V2 by V1 is 1 by 3. So here it will come 1, here it will come 3. Now if you calculate, then the answer that comes is 27 bar. To the next question, at what temperature will the 0.541 moles of argon gas occupy 10.21 liters of 1.75 at 1.75 atmosphere? So the number of moles of argon gas mentioned here is n equals to 0.541. It occupies a volume of 10.21 liters, and the pressure mentioned is 1.75 atmosphere. You want to find out temperature. So we will use ideal gas equation of state PV equals to nRT. Now what value of R you should use? There are two options you can do. Either you convert all this into SI unit and use R in the form of SI unit, and another option is you based on the values of pressure, volume and moles in what unit they are given, you choose a correct value of R. So here I will try to convert in SI and then do. Okay, so pressure is given as 1.75 atmosphere, which is nothing but 1.75 into 101,325 pascals. Now Pascal is the SI unit for pressure, so I am using SI units. Now volume is 10.21 liters. Now if you want to convert it into meter cube, then it is 1 by 1000 meter cube per liter. which is nothing but nRT. If you put up the values, then T equals to N is also given as 0.541 and R is nothing but, for SI unit it is 8.314. Now putting up the values and finding out the temperature, it comes out to be 402.5, which is option number C, 402.47. Moving forward to the next question. We have 56 gram of gas that occupies 38 liters of 700 mmHg. Now 700 mmHg, here this is pressure, which is in millimeters of mercury, because when you use a YouTube manometer to measure the pressure, it is denoted in the form of height of difference in the height of mercury and at temperature 15 degrees Celsius. Now you want to find the molecular weight. So again, using the ideal gas equation of state PV equals to nRT, you want to find out molecular weight. Now for that, what you will do, you will expand the you will put up moles as weight upon molecular weight. So how will you do? Mass M of gas divided by molecular weight into R into T equals to pressure into volume. Now you are given all the rest values and you just need to find out molecular weight. So molecular weight is nothing but mRT by PV. So again, what I will do is I will convert everything into SI unit. 56 gram into R is 8.314. Now I am not converting this gram into kg, which is the SI unit, because options you see it is gram per mole. Or if I convert this in kg, then what I will have is kg per kilo mole. So anyhow it will be gram per mole. So again, putting up the values, 15 plus 273.15. Don't forget to convert temperature into Kelvin. Then you have 700 mmHg. Now conversion for pressure is what? 1 atmosphere, or 101,325 pascals is nothing but 1 atmosphere, which is nothing but 760 mm of Hg. Now if you convert, then what will you get? 101,325 pascals represent 760 mmHg. Then for 700, what is the value? So instead of using 700 here, you will use the value of pressure as 700 into 101,325 by 760, which comes out to be 93325.6 pascals. So if you put up here into volume is given in 38 liters, which is 38 by 1000 meter cube. Now solving this, you will get the answer as 37.8 gram per moles. This gram per mole is the unit for molecular weight. Now, as per Dalton's law, the partial pressure of a mixture of ideal gas is equal to, now what does Dalton's law represent? So I have earlier discussed about Dalton's law in this lecture, and what does that state? The summation of all the pressures of individual components present in the mixture is nothing but the total pressure. Like Dalton's law states that pressure is additive. So if you add all the pressure, then the mixture will have total pressure. Van der Waals equation obeys the behavior of a real gas. Like, what is the meaning of real gas? Real gas is nothing but any gas which is present in the atmosphere, because none of the gas has ideal behavior, as I mentioned. Okay, so in that case, Van der Waals equation obey real gas, uh, and for ideal gas only, or when you have very low pressures, then only you should use ideal gas equation, and there is only one equation which is used for ideal gas, which is nothing but PV equals to nRT. For real gases there are many equations. Van der Waals equation of state is one of them. Moving forward to the next question, uh, you have 25 moles of O2 which is mixed with 175 moles of N2 at standard ambient temperature and pressure. Calculate the total volume of the mixture as per Amagat's law. So here you will apply two laws, like two formulas. One is ideal gas equation of state, another is Amagat's law. So based on the ideal gas equation of state, you have everything: moles, temperature, pressure. So you will get the value of V for O2 and V for N2. So that we can calculate from PV equals to nRT. So let's calculate that. So pressure of O2, like pressure is constant for both. Okay, so PVO2 equals to NO2 RT. So volume of O2 is nothing but NO2 RT by P. So if you put up the values, what comes out is 25 into 8.314 into 298.15 temperature divided by 10 raised to 5 pascals. So volume of O2 is nothing but 0.619 meter cube. Now moving forward for N2, PVN2 equals to N2 RT. So for N2, the volume comes out to be 175 moles into 8.314 into temperature is 298.15 divided by 10 raised to 5. So the volume comes out to be 4.338 meter cube. Now apply to find the volume of, like total volume of the mixture, we will use Amagat's law, which is Vt equals to V1 plus V2. Now first component here is VO2 plus VN2, and if we put up the values, what will come out as total volume is 0.619 plus 4.338, which is nothing but 4.95 meter cube. So the correct answer here is C. Now moving forward to the next question, Van der Waals equation reduces to real gas. Actually here it has to be ideal gas, because Van der Waals equation of state is for real gas, and if you want, like Van der Waals equation of state is P plus A by V square V minus B equals to nRT. Okay, so this is for real gases, and you want to find for ideal gases. So ideal gas is usually, you can consider any real gas as ideal gas when you have very low pressure, because at that moment the interaction between two molecules will reduce very much. So this term will be very less at that point of time, because this is nothing but interaction value, that is for interaction between two molecules. So since this value reduces, it will remain as V. You can, like, for this term you can it will be just equivalent to like just P. Okay, so it will be P, and so lower pressure always gives you gives the behavior of real tending toward ideal gas. Now if you decrease the temperature, then the gases tend to liquefy. So higher temperature always means that gaseous molecules will have higher energy and it will be far away. So high temperature also means tending towards ideal gas. So correct answer here is low pressure, high temperature. Next question is, for an ideal gas, the compressibility factor is dash. So if I use the generalized gas ideal equation of state for gas, any gas, it is PV equals to Z N RT. However, for ideal gas, it is PV equals to nRT. So the value of Z for ideal gas is 1. For any gas, compressibility factor is dash. Like you need to tell the range. So the options are actually not correct here. So the correct value is, it ranges between 0 and 1, because it is going forward to the next question. For the substance above its critical temperature, it exists as, so as I mentioned, critical temperature is the temperature above which there is no effect of pressure and you are not able to, irrespective of what pressure you apply, you are not able to liquefy that substance. So it will remain in gaseous form. Okay, so gas is the correct answer. Next question is, the temperature at which the gas no longer cannot longer liquefy regardless of pressure is, like I just told you the definition of critical temperature. So it is nothing but critical temperature. Next question is, gas can be converted into liquid by pressure only when its temperature is dash. So as I mentioned earlier, if temperature increases above critical temperature Tc, then gas cannot liquefy. So if temperature is less than or equal to Tc, then you will be able to convert any gas into its liquid form. So the correct answer here is the temperature T has to be less than or equal to Tc. Next question is, virial coefficients are the function of dash. So virial coefficients, they are function of temperature. So they are constant like B, C, D, which are related to temperature. So like there are correlations which relate this B, C, T, like I have mentioned somewhere. Yeah, so here you can see B naught is dependent on TR, like TR is nothing but temperature by critical temperature. So it is nothing but dependent on just temperature. So these are nothing but correlations which are derived based on some experiments, and some correlations are derived. So this is how it was observed to relate. So for virial coefficients, they are function of temperature. Now Peng-Robinson equation, the unit of B is dash, where B is the constant that is the correction for volume. Now this is the Peng-Robinson equation, okay, and these are the values of A and B, like how you need to find out A and B in this equation of state. So how we will find the unit of B? So for that, what you will do, it is very simple. Either you can check the formula and you can calculate the unit, or another way is nothing but Vm is nothing but the molar volume here. Now since both the values are subtracted, the unit of Vm and B has to be same. Now if Vm is molar volume, because you have not taken n into consideration here, so Vm will be molar volume, like V by M. So Vm will have unit of liter per mole. So similar unit will apply to B, because any two quantities of different units, they are not able to add or subtract. Okay, so they both should have same unit. Another approach is you have B equals to 0.0778 RTC by PC. Now you put up the values or the units of each and every term here, and like if you see PV equals to nRT, now RT by P has, what gives you RT by P? V by N. So it is nothing but V by N for critical conditions. So putting up the values or units of these parameters RTC by PC, which is nothing but having the unit of V by N, that will be liter per mole. Next question is, using the virial equation, calculate the specific volume of CO2 at 310 Kelvin and pressure at 7 bar. You are given the correlation for Z and the non-ideal equation of state. So there are some more units that or the correlations that you need to use. So one of the correlation is wait, I will tell you what are the correlations that you should use for B0 and B1. So for B1, B0 it is 0.083 minus 0.422 by TR power 1.6, and B1 is 0.139 minus 0.172 divided by TR power 4.2. Now based on this correlation, you will calculate the values of B0, B1, which you will substitute here and find out the value of Z. Now so first let's find out the value of TR and PR. TR is what? T by Tc. So critical temperature and pressure are not mentioned here. So that you need to find out from any of the appendix which are available in the thermodynamics book. So one of the book I would suggest is you can refer to Smith and Venus book, and in the appendix you will find the values of Tc and Pc. So Tc for CO2 is 31.1 degrees centigrade. PC is 73 atmosphere. Okay, so TR will be 310 divided by 31.1 plus 273. For division also you need to have same unit. Okay, so if you do that calculation, so the value of TR comes out to be 1.018. Now since it is just the ratio of two temperatures, TR is unitless. Finding out PR will be P by PC, which is at 7 bar divided by 73 atmosphere. So either you convert 7 bar into atmosphere, or you convert 73 atmosphere into bar. So I will tell you the correlation for bar to atmospheric conversion. 1 bar is 1.01325 atmosphere. So if you have 7 bars, what will be atmosphere? So you can calculate and put up that value here. So that is nothing but 7 into 7.0 7 into 1.01325. which is nothing but 7 point, sorry, this is 7.09 divided by 73. So the ratio of these values gives you the PR, which is nothing but 0.097. Now moving forward, what else do you need? You need to calculate B0 and B1. So if you put up the value of TR in both the equations, what you will find out for B0 and B1 is B0 will come out to be minus 0.3273 and B1 will come out to be minus 0.0208. Now you need to put up these values in this equation, compressibility equation. Z equals to 1 plus B0 plus omega B1 PR by TR. Okay, so omega again here is eccentric factor, which is a constant. Okay, so there is one formula also for finding out omega, and you can prepare a chart. So values of omega is also available in the appendix, and you can check for that. And value of omega for CO2 is 0.224. You can check out the appendix and take this value. So if you put up all the values, uh, the value of Z will come out to be minus second, point 968. Now if you put value of Z in this equation, non-ideal equation of state, V equals to ZRT by P into molecular weight. Molecular weight of CO2 is 44. If you put up all the values, try to use it in SI or some value of R is given as 83.14. Now you need to use pressure in atmosphere. So take the pressure as 7.09 atmosphere, which we calculated earlier. Molecular weight is 44. So answer is 78.45 centimeter cube. It has to be per gram. Okay. Now the unit also mentioned in this question, like in the options, are wrong. It has to be centimeter per gram, and there is no option which correctly matches the actual answer. So you can correct this question and you can update your solution. Moving forward, the formula for eccentric factor is represented by dash. So the formula for eccentric factor is nothing but this formula. The formula for critical temperature Tc is expressed where dash. T is temperature, Tc is critical temperature, and Tr is reduced temperature. So reduced temperature is always represented as the ratio of temperature to the critical temperature. So critical temperature is nothing but T by Tr. So that's it from my side. If you have any doubt, you can tell me, or we will stop the session. If there is no doubt, we can end this meeting. So thank you. I will stop the sharing.